Now, last Friday, there was probably some things put up here, really had you concerned. Didn't understand it, but I'm going to try to make sense of all of this. And if you pay attention, it won't be hard. All right. Really what I did is said that anytime we're evaluating transfer phenomenology at a constant frequency, either a cosine or a sine variation, we can turn these differential equations into algebraic equations and solve them. Now let me show you what this means practically speaking. If we think of an inductor, L, as such, and we have a current I in that inductor, it causes a voltage V across the inductor that says basically the equation is V is equal to L times di dt. Now that is in the time domain, it's a differential equation. Do y'all follow me? Remember, we were moving into what is termed the phasor domain. We're going to assume instead we have cosines or sines, we have this e to the j omega t as the forcing function. So here's what happens. If we assume I now, since I know we're going to, I'll do it in the time domain, it's going to have a forcing function that the current will respond at the same frequency as the voltage, but it'll be some I naught e to the j omega t. Y'all follow me? Now, remember, e to the j omega t is a cosine of omega t plus j sine of omega t. We only care about the real part, but just bear with me. That means V is equal to L times the time derivative of I right there. Do y'all follow me? The time derivative of I would just bring out the j omega. Do y'all see that? If you take a derivative of this with respect to t, only the j omega comes out. So it's going to be this times I naught times j omega times e to the j omega t. And maybe I should do, I can call this small I if that bothers you. Y'all with me on this? It's an assumed solution. I'm assuming the form of the solution, everything is going to vary in time at the same rate. It has to. It's the linear differential equation. Now, if you look at this, I know that V will have the form of some V naught, right? It could have an angle, and it's going to be e to the j omega t. Y'all with it? It varies as the same way as the I. It has the e to the j omega t. Y'all follow me on this class? Let me see your hands if you do. You may not like it, but you're going to in a second. It'll beat the heck out of solving Diffie Qs. Remember with RC circuits? I didn't make you solve Diffie Qs for Laplace. I gave you the known solution, you just solve for constants, right? This gets even better. So now, if I take that and I say this is V naught e to the j omega t here, now I want you to see something here. There can be a phase, but don't worry about it. You see how the e to the j omega t cancels? That's the first point. They always will. You with me? It's gone. It will not exist. So we know it's called suppressed. And when I take a look at the ratio of V naught to I naught, it's really going to be j omega L, right? And this right here is going to be very important. Everything else cancels, and I get the ratio of voltage to current is j omega L. You with me? I'm going to say this. Remember, j is a complex number. Technically, it's a square root of -1, but really, it's a construct to help us solve problems. Think of it as an intermediate step. Now, this is called the inductive reactance. And the symbol is usually X sub L. What I like to say, it is a complex resistance. So if you give me a frequency of operation, tell me the frequency and F, omega would be 2 pi F, I can tell you this value. You all follow me on this? Now this is going, you're going to see how come it's important. And likewise, let me erase this part. This is for an inductor. If we have a capacitor here, we know it develops a voltage V for a current I, and we know C times dV dt is equal to I. That means the time varying rate of change of the voltage across the capacitor is the current that's actually going to go right through that capacitor. That's the definition of current voltage relationships in a capacitor. A capacitance of constant value. You with me, class? Now, when we do the same thing here, we assume both voltage and current vary as e to the j omega t. Just with me on this, class? Here's the real thing that happens. Every time there's a time derivative, a j omega pops out, and the e to the j omega t goes away. So we don't keep on doing that over and over again. And we find here that I naught e to the j omega t, and actually, why don't you just call this x sub L? Don't even put that in here. Call this, it's the inductive reactance, is equal to C times j omega times V naught times e to the j omega t. Here the derivative was on the voltage, not the current, so there's a j omega that pops out there. Y'all see this, class? It won't be that bad. How many see this right here? Yeah, right here, you're taking the derivative with respect to time to voltage, right? Of the voltage. The voltage is going to be V naught e to the j omega t. Who asked this? All right, do you see it right there? Take a derivative, you're just pulling out the j omega, right? All right, now if you look at the ratio of V to I here, this will be called the capacitive reactance. And what it'll be is 1 over j omega c. I'm going to make one more comment. Y'all with me? Don't freak out about this. It won't be that bad. Now, what is 1 over j? Can anybody tell me? 1 over I for MEs and AEs. Let me put this up here for everybody. When you see j, that's the what we use to it's the mark, or really how we label an imaginary number. It was with the j coefficient. All right. What that is like the I coefficient in math or an AE or ME. All right, with me on that? I think probably industrial too. So when we talk about j, you can say it's 1 at an angle of 90 degrees. That's true. You can say with j, it's equal to e to the j pi over 2 radians. It doesn't matter how you do it. That's j in a nutshell. But if I have 1 over j, I'm just trying to make this point one time and clearly make it. That's really 1 over 90, right? Or 1 over this. How many see that's equal to minus j? How many see that? Sure. Right, class? 1 over, just take 1 over 90. That's 1 over 1 at an angle of 90 is the same thing at 1 at an angle of minus 90, isn't it? The angle inverse. How many see this, class? You guys surely have to, right? So I can rewrite this as simply minus j over omega c. What I like to do is talk about this, the capacitive reactance and the inductive reactance. They're just like resistances. The ratios of voltage to current in an element, only now they have an imaginary context to them. With me? Now I'm going to show you how this applies to solving a problem without going through and writing the Diffie Q every time and then going ahead and putting in the assumed solution and canceling the e to the j omega t's. That stuff gets old and very quickly, and you don't need to do it. So here's how you apply it. Now please follow me in this and watch, and you'll see. So here's my circuit. I'm going to have a voltage source, V naught times cosine of omega t plus, say, 30 degrees. Now, technically, this is kind of a wrong way to do it, but it's done in the book. You see, omega t is usually in radians. Omega is radians per second times t in seconds would be radians. You can't mix radians and degrees. Really, this should be pi over 6. But in the book, he puts 30 degrees because we're going to reduce this to something where it's just magnitude at angle. So that's the voltage. Let me try to make that a little clearer and bigger. All right, that's the voltage. Can you all see? Now I'm going to go ahead and I'm just going to create a series circuit. I'm going to start with a resistance R, and I'm going to have an inductor L, and I'm going to have a capacitor C. What I'm after is the current through here, but I want the current in the time domain. I'm just going to erase all this. And I'm going to put down two things up here. Remember, for a capacitor, this thing has an impedance. Think of it as an impedance, complex impedance Z, as 1 over j omega c, or minus j over omega c. And for an inductor, L, this thing has an impedance Z equal to j omega L. All right? Go with me?
That's j omega c up top? Or is it j omega L?
No, this is 1 over j omega c for the capacitor. Can you see it okay? And this is an inductor, so it's j omega L. And it's simply a ratio of the voltage to the current. So it's like a resistance. Think about resistances. What is it? Without you thinking too deeply, it always tells you the ratio of voltage to current in that element, right? Yeah.
Earlier you called it inductive and capacitive reactance. Is it now?
And impedance is the same thing, only reactance emphasizes there's no real part. I don't really, that's the last thing you read, is that word, all right? Now, getting back to this, here's how we solve this. You ready? This was in the reading. If you looked at your books this weekend, this was exactly what I showed you to read in the book you purchased for this course. So what happens here is, we take this problem and we go out of the time domain and into the frequency. You see this right here? That source becomes this. It's just going to be V naught at an angle of 30 degrees volts. No cosine business. All that's suppressed. All right? And I try to show you that on Friday, and I could go through it, but it isn't going to help you to just understand the beauty of this. It is suppressed. I don't think it is. So now there's a resistor. Well, the resistor can be a resistor. They don't change in the frequency domain or the time. This is called the phasor domain. Some people call it the frequency domain. Over here. Now there's an inductor. We replace the inductor with its impedance or its inductive reactance, j omega L. All right? It's just like resistance in terms of what we're going to do with it. Then there's a capacitance. And the capacitor here has an impedance of 1 over j omega c, or minus j over omega c. And then you have this. Now this is in the phasor domain. And I know this can be a little bit disheartening because you get a little concerned. I haven't seen this before. Don't worry, it won't be bad. Now, the current we're going to find is going to be a phasor current, I. You want to put a little tilde over the top, you can. That's how it is in Dr. Gross's book. Are you with me, class? Remember, you all see the transform. All you gotta do with the voltage is take the magnitude of the voltage and the phase angle inside the cosine argument, right? Over here, I replaced the inductor and capacitor with its impedance value. Y'all follow me? Now, when we want the current I, do it as if they were real resistances. If we had a voltage right there and you wanted the current, do y'all see they're in series? What would you do? You would take V naught at an angle of 30 degrees, and you would divide it by R, right? And then it would be plus J omega L. Look at it this way. Are you with me? Here, I just took the J out in front of those last two terms, and I know it's going to be omega L minus 1 over omega C. Can you all see this, class? How many can see this okay? You understand this? Now, here's the thing. That's a complex number. That will be a complex number, depending on the value of omega, L, and C, and R. Now, I have to ask you a question, because I'm going to have to do a bit of review. How many have had complex numbers? Everybody in here is supposed to have had complex numbers. Whether you admit it or not, or even understand what it means, you've had real and imaginary parts to your numbers, haven't you, class? Surely in math you have, right? Sure, you may not like the idea, but you have been exposed. I'm going to show you how it applies, why it's important to understand this to solve problems. Now, I'm going to get to do a little review of that complex numbers, but do you all see with complex numbers, this ultimately is going to be some magnitude, and I'll call it just I naught at some angle, and I'll just call it theta sub I. I want to finish this, then show you. Okay? It's going to have a magnitude and angle. Everybody follow me on complex numbers? You can either have real and imaginary parts or magnitude and angle. You want me to write it bigger? I'll be happy. This is going to be some I naught at some angle theta sub I. It's the angle associated with this ratio. Got it? This is in the phasor domain. That's still valuable. You got magnitude of I naught, usually you want. In the time domain, I'm going to put it over here. If we go back to the time domain and I wanted I of t, you simply take the scale value, the I naught, the magnitude. Then you repeat the cosine of omega t, and then you add this angle. And now you have, now this is not the transient form. If there's a switch to turn this on, there's going to be a time before this thing is the steady state response. But now you have the magnitude, you have the cosine of omega t plus the phase angle, and that will be the response to the current. Y'all follow me on this, class? Of the current to that voltage. When you go for your interview, at some point you go to a power company, some of you IEs especially, they're going to give you something like this. They won't give you this. They'll give you an L, and they'll give you a C, and they'll give you a constant voltage there. At a frequency with a given magnitude, like a 10 cosine of 377t plus 12 degrees. And they want to see if you understand how to get the current. Now the reason is, if you're just a physics person, you've got to write a DiffEq. And that will alert them to the fact, don't put you out there in the field, because you might destroy something. So, but if you're an engineer, and they see you doing this, you're the guy or the gal that they want to do this stuff. I'm just being on level with you. I'm not against physicists, but I know what I'm talking about when I say physics has a different philosophy. There's elegance and beauty and great, formulations that are differential equations based. Not a lot of appreciation for simplicity here. So now, getting back to it, you want to see something with real numbers, probably. And before I do that, I want to do a quick review of complex numbers. The reason I want to do this is I have taught this class before, and my assumption that everybody is familiar with them is not valid. I mean, there are people that are completely oblivious to some basic facts. So I want to make sure you see this, then we'll get back to this. So really, complex numbers, don't let them ever scare you. What they really mean is they have a real and imaginary part that means nothing until you take that information and bring it into the time domain. But they're needed as something that contributes to the solution. When we talk about complex numbers, say we have A, and it's going to be equal to some small a plus JB. Remember, J is the imaginary symbol. What it really represents is, graphically, if this is the real axis and this is the imaginary axis, then I'm out A on the real axis here, and I'm up B here. And this line would represent what A is. Can you all follow me on that, class? Everybody see that? This is just a graphical representation. The imaginary axis is vertical. The real axis is in this direction. A has no J in front of it. It is a real number, like 10, 12. The JB, J times anything, if B was 10, that would be an imaginary value. Y'all with me on this, class? Now, that's equal to the square root of A squared plus B squared in magnitude, and it's at an angle equal to the inverse tan of B over A. I'm just going to mention this, because if you're ME and AE, if you work with this, don't worry about it, but you should see this. I'm talking about this angle right here, right? This is the angle that is right here. That angle, if you think about opposite, this is B over adjacent A, is the tangent of the angle, right, in ratios? So that's the angle. What I'm really saying is this is equal to a magnitude of A, and it's at some angle A. This is called polar form. It's a magnitude at an angle. Are you with me? Now, this form is also often rendered as simply magnitude of A e to the j theta. And the only reason they do that is called exponential notation. It's closer to the actual way. It's easier to merge with the forcing function e to the j omega t if you want the real value in the time domain. But don't worry about that. These are all the same. They all have the same meaning fundamentally. Got it? Now, if we add two complex numbers, if you have A is equal to A plus JB, and B is equal to C plus JD, we're going to just add them. So if we add A plus B, the only thing that happens is you add the real components, A and C, and the imaginary components. Do y'all remember that? You remember doing this, class? This is like basic stuff, but I often worry that some people don't remember. I have that. That's addition. Can you all follow me? If there's subtraction, there would be a minus sign there. Are you with me? It's nothing tricky here. Now, you add the reals, you add the imaginaries, or you subtract the lower real from the upper real, if there's subtraction. Now, multiplication is a little different. I prefer to do multiplication and division in the actual polar domain. This number A, I said was already that or that. And B, I might as well just say B is equal to the square root of C squared plus D squared at an angle tan minus 1 of D over C. And this is really, call this theta A, and call this theta B. So then if we had A times B, it would be equal to, let me put it this way. magnitude of A times magnitude of B, but then it would be an angle of theta A plus theta B. Y'all follow me? You're adding the angles now, multiplying the actual magnitude. Follow me, class? How many remember seeing this? You'd get it with exponentials real easy. If I did it this way, you would see A times B, right, magnitude, and then you would add the exponentials. Do you follow me, class? All right. If I have A divided by B, it would be magnitude of A, just the magnitudes, over magnitude of B. And it would be the angle of theta A minus theta B. Now you can do multiplication with, these are called rectangular components, with real and imaginary components. But there's a little more work to it. That's the only reason I do it this way. I want to give you a concrete example of each of these before I continue, okay? So follow me on this. So if I have A equal to 1 plus J2 and B equal to 2 plus J3, what is A plus B equal to? Just look. Class, can y'all read that or not? What is it equal to?
3 plus J5.
So you're adding the reals, 3, go ahead,
Plus J5.
plus J5. Y'all agree with that? Can you see it in the far back? What is A minus B? One minus 2 is minus 1, right? 2 minus 3 is minus J1. Y'all agree with that? All right. Now, what is A times B? These are complex numbers. This takes a little doing. I should have picked something easier. This is what? This magnitude is 1 squared plus 2 squared, or really it's 4 plus 1, a square root of 5, right? The angle here, I'm just going to call it theta A, right? That's equal to tan minus 1 of 2 over 1. I'm not sure what that is. Anybody know off the top of your head? I'm glad I'm not the only one. It's an angle. Call it theta A. Here, this one is going to be what? Square root of 2 squared is 4, 3 squared is 9, right? So what? Square root of 13, do you agree with that, class? Sure. Square root of 13, and this would be at an angle of, call it theta B, which would be equal to tan minus 1 of 3 halves. Right? You agree with that? Now, if you wanted A times B, it would be square root of 13 times square root of 5. And then it would just be the angle theta A plus theta B. I wish I had the actual angles down. And then A over B is simply equal to square root of 5 over the square root of 13. And here it's going to be at an angle theta A minus theta B. Now that's really in a nutshell what you need to know. Okay, about complex math. You with me, class? We could go on about things, but that's it. Adding, subtracting, multiplying, and dividing. Next, now that I've shown you that, I'm going to give you a practical example. You ready? I want you to get a good sheet of paper, clean sheet, and be real attentive. Because I'm going to do something where I'm not going to put down omega and then you calculate omega L and 1 over omega C. I'm going to give you those values. So I want you to be real attentive here. I'm erasing this. All right. So now we're at constant frequency. Things vary as a cosine of omega t, right? In the real problems, I mean the solutions that you're going to see most problems stated in this area, they don't even give you the omega. The only thing they care about is the phasor form of the currents or voltages. Now let me show you a practical problem. Here, this is typical. They assume everything varies as cosine omega t. So right here, they might have 10 volts at an angle of 30 degrees. That's a voltage source. Do y'all follow me? It is, we know it's in the phasor domain because this angle doesn't appear at constant DC, all right, constant voltages. This is a phasor form of a problem's, really its interpretation. Now I'm going to put a resistor here, R equals 100 ohms. And then I'm going to put an inductor here. And I'm going to say the inductance reactance is J100 ohms. Can you all see this in the far back too? Gotta make sure. Can y'all? All right. And what I want is this current. Now, we treat those two elements as if they were just regular resistances, except this one is complex. All right. Now, pay attention. So that means this I, and this will be in the phasor domain. I phasor will be equal to the voltage. Can everybody see? Normally, if this was just a real resistance, that a real voltage source, if I wanted this current, I would take the voltage divided by the sum of those two resistances, right? Same deal here, only now we put the J's in. Divided by 100 plus J100. Can you all follow me? Now, I'm going to make this bottom, by the way, your calculators do this for you, which is nice. But you need to see this. Calculators are wonderful when it comes to getting to the bottom, getting to the answer. So here, I have 10 at an angle of 30 degrees, divided by, well, this is really what? Square root of 2 times 100 at an angle of 45 degrees. Do you all see that? 100 plus J100 is really 100 times square root of 2 at 45 degrees. Can I see your hands if you understand it, so I know I'm talking?
How did you get to that?
If you have 1 and 1 here, the hypotenuse of square root of 2, isn't it? Who asked this? Y'all, do you agree with that? All right, well, 100 and J100 is like what? Right? And this angle would be 45, wouldn't it? I mean, I assume that you understand if you're 100 over, 100 up, it's 45 degrees, right?
Are you assuming that the I just means that it's in an X direction if it doesn't have?
It's
like
perpendicular. When you graph this thing, the J is like the Y-axis.
Okay, and so anything without a J is just considered an X-axis?
A real number. The reals are usually horizontal. The imaginary is vertical. That's it.
Okay, but like, what about if we're talking about the voltage here?
The voltage at 30 degrees, if you wanted to actually graph it, if this was the real axis and this is the imaginary, this would be 10 at an angle of 30 degrees. That's what that means. It's in the complex plane. So this is the imaginary or J-axis. This is the real axis.
And then X-axis is
the real
higher.
values. The real values.
Okay.
Now the projection onto the real axis, by the way, is the cosine of that value, and it's the cosine. Well, I don't want to go there yet, but there's a lot of interpretations that can be made. For now, do you all understand this right here is representative of what's going on here, and that's representative there? How many see that? You all see it in the back? All right, now, what is this going to be? Well, this is important you see this. I got an angle of 45 in the denominator, right? Can you get that? When I go to the numerator, it becomes minus 45. How many see that? All right, sure. This becomes just 30 minus 45 degrees. I'm going to leave it as that. You all see this? Right? 1 over 1 at an angle of 45 is really 1 angle minus 45. Correct, class? Now, keep going on that. What does this become? Well, 10 over 100 divided by square root of 2. You might as well put down 1 over the square root of 2 times 10 right here. And if you like, you can put down what? 1 over 14.1414 if you're so inclined. But you all follow me on this. Square root of 2 divided by 10. And what's the angle going to be? Class? Just minus 15 degrees, all right? Now, I didn't make you calculate, I didn't give you an omega and an L separately and an C or an L separately where you had to take omega L and see this is the value. This would be, omega L would be the 100, you follow? I don't care what omega is. I want you to see this. Now when I go to the time domain, I of t will have that magnitude, so it'll be 1 over square root of 2 times 10, and then it will be the cosine of omega t minus 15 degrees. And that, in fact, would be the time varying current. It would be in amps. So now, without writing one Diffie cube, this is called the steady state solution. And when you had your mathematics courses and differential equations, there was the steady state or forced response, and there was the transient response. Right? This is going to be the steady state response after the transient dies out, if there is.
Is the cosine in the numerator?
Couldn't hear you.
Is the cosine in the numerator? Is that all the
Yeah, it has to, it will vary. Remember, I said this is equivalent to really 10 times cosine of omega t plus 30 degrees. Remember that? I didn't want to keep going on this line, but really I of t is equal to the real part of the phasor we just calculated for I over there, times e to the j omega t. That's how you get it, but you always get a cosine of omega t plus the phase angle. All right, phase angle is minus 15. Always going to be that. So then it's going to be cosine here of omega t, right, minus 15 degrees. Now, by now you're looking at this and saying to yourself, wait a second, this isn't really that tricky, it's just what we've been doing, only now we have that J guy, that complex number, and that's it. And what you're really going to be asking for most of the time is this, just the magnitude and angle of either a current or a voltage. Remember before? All your problems ask for either a current or a voltage at a given point in a circuit, right? It's the same thing here. And all the theory and all the stuff you've been exposed to, Thevenin's analysis, source transforms, nodal, mesh, all those things can be used for these problems. You got me on this, class? It really, I don't know how they teach it when other people teach this. If you're sticking to the, just the book, you get, gosh, it's rough. But I'm trying to just show you it is not that mysterious. This is the essence of what goes on. The capacitors become minus J something. The inductors become plus J something. I want to work another problem. All right? I got a little time. By the way, in the book, and I don't do it this way for everybody, they do the complex stuff at the same time they do mesh, nodal, and all that stuff. And it gets confusing. I don't know if they teach it that way, but if you do that, you're going to confuse the heck out of a lot of students. All right. Now, remember I said everything applies to, we use the same exact stuff we've been doing all the time, only now we have complex impedances. That's the way I like to think of it. So, honestly, the best way to learn this stuff is just let me show you a few problems, then you'll get it. And you will not have to, just angst about, what about that e to the j omega t? So, let me just calculate the equivalent impedance of things. Now remember, I like to give you the omega L multiplied together and the 1 over omega C, so the value itself. So if we take a look at something like this. This is, you'll see these tonight, 411, and I have a capacitor, and then I have a resistor, and that's 2 ohms. The capacitor is minus J 2 ohms. This is going to be 4 ohms, and this is J2. And the only thing they want is the equivalent impedance right here. And it's called an impedance because we're in the phasor domain. And this is just getting you comfortable, or at least familiar with techniques. They're going to be used all the time. So, let me ask you this. Do you see these two are in series? How many do? Those two are in series, and those two in series are in parallel with that, correct? So what I'm going to do is say if these two are in series right here, this is equivalent to 4 plus J2 right there. Just showing you, okay? And if you have two impedances, I'll call it Z1 and Z2 in parallel, and you want the parallel equivalent right here, it can be gotten as 1 over Z1 plus 1 over Z2, or it can be Z1 times Z2 over Z1 plus Z2. The second one comes for just multiplying the top and bottom of this equation by Z1, Z2. Can you all see it? So let's use this equation so that we find the equivalent from here over. I want to find Z prime. In other words, just from this point and this point over, I want to find out what that is. So that value of Z would be equal to the first impedance 2, I'm doing it this way for a reason, times the second, 4 plus J1, or J2, pardon me, over the sum of the two. So it's 2 plus 4 plus J2. Y'all follow me in this class? I want to make sure y'all can see in the back. Good? All right, what is this going to be? Standard rules of math apply. That's 8, right? Plus J4 over 2 and 4 is 6, right? Plus J2. You agree with that? Here's what I want to tell you. If you want, if you put this in your calculators, you can get this in a real and an imaginary part. The way it was done historically long ago, they would multiply top and bottom by a complex conjugate. How many have heard of the term complex conjugates? All right, so what they do is say, I'll multiply both of these by the conjugate of this. Conjugate just means, and this is something I better say, whenever you talk about a conjugate of something, if A is 10 at an angle of 30 degrees, A conjugated, that's the symbol used a lot of times, is minus 30 degrees. The angle changes. Conjugation also means if it is not magnitude and angle, you simply flip the sign on the imaginary part when you take the conjugate. So a complex conjugate multiplication starts down here, and you take it and you simply multiply top and bottom by the conjugate of the bottom. It's called the complex conjugate of the bottom. You with me, class? Now the reason I do this is I get a strict rule here. So then you multiply the top, and I'm out of time. But you can see I'm going to get this times this, which is going to be what? 6 times 8, 48. Then I get J24. Then I get minus J16. Then I get J times minus J, which is what? J times J is minus 1 over minus is plus 1. So I get plus 8. All divided by this, which ends up going to be what? It's going to be 6 squared or 36 plus 4, or 40. I'm gonna just leave it right there. I'll pick it up next time. I've got 1 minute over, but I wanna tell you, it won't be that bad. Please, I'm gonna give you some homework. Do it. If you got questions, send me emails or something, and I'll try to answer it. But don't be afraid of this stuff. Now, the way it's been taught, I don't know if it's taught here this way, people try to lump all this stuff together when they do circuit analysis, the complex numbers and all that. If you've ever had it that way, it's probably very confusing. You don't want it that way. You want to separate from what I'm doing.